Well, hi everybody, welcome back. In the last video, we defined something called the complex exponential, and we said that the complex exponential had a domain of purely imaginary numbers, so it was I times a real number, and that the range of that function was the complex numbers. And we used it to write z as r e to the I theta, and e to the I theta was defined to be cos theta plus I sine theta. So it was a neat way to write a complex number that was written in polar form. But it's also really great for calculations when you're doing calculations with complex numbers, because it has the same properties. The complex exponential has the same properties or similar properties to the real exponential function that you know. And we're going to go through some of these properties and show you why that works. So in the first property that we're going to look at, you'll recall that the real exponential function that you already know has the following properties. E to the naught is equal to 1. E to the x times e to the y equals e to the x plus y, and e to the x over e to the y equals e to the x minus y. So those properties are really useful, and it turns out that the complex exponential has similar properties. So let's look at property 1 for a second. So this says that e to the I times 0 equals 1. So this is similar to this property of the real exponential function. Why is that true? Well, we defined e to the I theta to be cos theta plus I sine theta, but our theta is just 0, so we're looking at e to the I 0 is cos of 0 plus I sine of 0. And we know that cos of 0 is just 1 and sine of 0 is 0, so that's I times 0. So e to the I 0 just equals 1. So now we're going to look at property 2 and show you why it works. So property 2 says e to the I theta 1 times e to the I theta 2 equals e to the I theta 1 plus theta 2. So that's analogous to this result here. So e to the x, e to the y equals e to the x plus y. Okay, so what we're going to do now is we're going to try and prove property 2, and property 2 from the previous page said that e to the I theta 1 times e to the I theta 2 was equal to e to the I theta 1 plus theta 2. So multiply the complex exponentials together means add the arguments. Okay, what are we going to use to prove that property? Well, we're going to use the compound angle formulas for cos and sine that we looked at in topic 1. So you'll recall from topic 1 that cos theta 1 plus theta 2 is equal to cos of theta 1 times cos of theta 2 minus sine of theta 1 times sine of theta 2, and sine of theta 1 plus theta 2 is equal to sine theta 1 cos theta 2 plus cos theta 1 times sine theta 2. Okay, so there's quite a few terms there. Let's just break it down and see what it looks like. So we're starting off with e to the I theta 1. So by definition, that's cos theta 1 plus I sine theta 1. And e to the I theta 2 by definition is cos theta 2 plus I sine theta 2. And we're going to multiply those two brackets out and see what we get. Okay, so in the first instance we take cos theta 1 times cos theta 2, gives me that term there, and then we're going to take I sine theta 1 times I sine theta 2. So I get the sine theta 1 times sine theta 2 terms here, And don't forget also we've got an I in this term and an I in that term, so that gives us an I squared, but I squared is just -1. So that product becomes minus sine theta 1 times sine theta 2. Okay, so I've done that term and that term. Now I'm going to multiply cos theta 1 by I sine theta 2. So that gives me I times cos theta 1 sine theta 2. And what else do I still have left to do? I have to multiply that term by that term. So I get I sine theta 1 times cos theta 2. So that's all the cross multiplication, all collected together in these two brackets. So let's have a look now and see what we have. So in this bracket, well, let me just rub off the writing for a minute so you can see this better. Okay, so in this bracket we've got cos theta 1 times cos theta 2 minus sine theta 1 times sine theta 2. And if I go up here and look at my compound angle formulas, you can see that that's just the same as this right hand side of this equation here. So this expression I can write as cos theta 1 plus theta 2. On the other hand, if I look in this bracket, I've got cos theta 1 sine theta 2 plus cos theta 2 sine theta 1, which is just the right hand side of this compound angle formula. So I can replace this expression by sine theta 1 plus theta 2. So if you look now at what I've joined these two expressions together to give, I've got something that says cos of phi plus I sine of phi, which is just e to the I phi, and my angle phi here is just theta 1 plus theta 2. So if I put that together here, this is just e to the I theta 1 plus theta 2. So that's exactly the expression that we were trying to show was equal. Okay, well, why is that important or interesting? Well, think about multiplying now two complex numbers together, Z1 and Z2, where Z1 is written in complex exponential form and so is Z2. So this product now becomes R1 e to the I theta 1 times R2 e to the I theta 2. So we've got the product of two real numbers here, so we can bring those two things out the front, R1, R2, and then we've got e to the I theta 1 times e to the I theta 2. So this property 2 of the complex exponential says that what I can do with that product is write it in this form, e to the I theta 1 plus theta 2. So that's what I've got here in the box. So if we have two complex numbers written in exponential polar form and we multiply them together, we can see what happens on this side. So if R1 was equal to the modulus of Z1 and R2 is equal to the modulus of Z2, then multiplying the two complex numbers together, on the right hand side we can see that what we've done is we've multiplied the moduli of the two complex numbers together, so that Z1, Z2 in modulus is equal to the modulus of Z1 times the modulus of Z2. And if the argument of Z1 is theta 1 and the argument of Z2 equals theta 2, then multiplying the two complex numbers together means that what's happened in the product is I've added the angles. So the argument of Z1 times Z2 is equal to the argument of Z1 plus the argument of Z2. So have a go at this example at home. Think about what happens geometrically when you take some arbitrary complex number and you multiply that complex number by w when w is the complex number I. Okay, and we'll talk about it when you come into class on Thursday. Okay, so there's a couple more questions then that you can go ahead and do now. Try them for yourself at home. So that homework question is doing the same thing but multiplying an arbitrary complex number by -1 and thinking about what happens with that geometrically. And the next thing that you can try doing is to develop this relationship. So we saw what happened when Z1 and Z2 were multiplied together using the compound angle formulas. Try a similar approach, but instead of multiplying them together now, we want to divide them, Z1 over Z2. So have a go at that at home, and we'll talk about that when you come into class as well. What you'll find is that the interpretation of that quotient that you find is that when you divide two complex numbers now and you take the modulus of the quotient, it's the same as the modulus of Z1 over the modulus of Z2. And when you take the argument of Z1 over Z2, it's the same as taking the argument of Z1 minus the argument of Z2. And knowing those basic properties is going to make calculations in complex numbers a whole lot easier. So have a go at the next example. There's a couple of examples there for you to try, and again we'll talk about when you come in on Thursday. Okay, and on the next page you've got a nice list of the results that we've just shown. Then a couple more examples for you to do. And you can then start doing some more examples from the handbook from this section in topic 3. Okay, so that's the end for this video. When we return for the next video in the series, we're going to start thinking about how we might sketch some regions in the complex plane. Okay, have fun with it.